Today's topic is ionosphere. Ionosphere is the upper part of atmosphere extending from 70 km to 400 km above the Earth's surface. This part becomes ionized by getting energy from ultraviolet radiation, gamma radiation, and cosmic rays coming from the sun. So, the region from 70 km to 400 km above the Earth's surface, it is ionosphere. Here, the gas becomes ionized by this radiation, ultraviolet radiation, gamma radiation, and cosmic rays, which is coming from the sun. By ionized medium, we mean that the electrons and positive ions are produced. If a gas becomes ionized, then electron and positive ion pairs are produced. So in this ionized medium, in ionosphere, we have electrons, positive ions, and some neutral atoms. According to Edward Appleton, there are different layers of ionization at different heights, D, E, F1 and F2 layers in ascending order of height. So, these are the different layers, which this name is given D, E, F1 and F2 layers, which are ionized layers. These layers reflect the radio waves of high frequency coming from the Earth's surface and sends back to Earth. So this ionosphere plays an important role in the propagation of radio waves, in transmitting the radio waves from one place to another. First, we will find the expression for permittivity and refractive index of ionized medium. In ionosphere, there are positive ions, electrons, and neutral particles. This medium affects the propagation of radio waves. We consider the propagation of radio waves in this ionized medium by neglecting the effect of Earth's magnetic field and assuming that the collisions with the neutral particles are negligible. Radio wave is an electromagnetic wave in which there are periodic vibrations of electric field and magnetic field. Due to periodic electric field, E equal to E0 sin omega t. In electromagnetic wave, radio wave is electromagnetic wave, and in electromagnetic wave, electric field E and magnetic field B, these are oscillate in this way in periodic manner as E equal to E0 sin omega t. E0 is the amplitude and omega is angular frequency. If f is frequency, then angular frequency omega is 2 pi f. So, periodic vibrations of electric field are given by this formula E equal to E0 sin omega t. Due to this electric field, electron experiences a periodic force. Force acting on electron due to this electric field E will be given by F equal to minus EE. Minus E is charge on electron and capital E is the electric field. So this force will become minus E0 sin omega t. This is a periodic force, and due to which electron vibrates with angular frequency omega. Here E0 is the amplitude of the periodic electric field. If mass of electron is m, according to Newton's second law of motion, its equation of motion is given by this formula. Equation of motion for electron according to Newton's second law of motion is given by this relation m dv upon dt equal to f. Mass into acceleration equal to force, and acceleration is dv upon dt. So m dv upon dt will be equal to minus E0 sin omega t. Minus E0 sin omega t is the force acting on electron due to this oscillating electric field. Now from this equation we write expression for dv. dv will be equal to minus E0 upon m sin omega t dt. And if we integrate this equation, then integral dv is equal to v, and in right hand side minus E0 upon m is constant taken outside the integral, and integral sin omega t dt will be equal to minus cos omega t upon omega. And c is constant of integration. So correct here, this v will be equal to E0 upon m omega cos omega t plus c. The term before cos omega t is E0 upon m omega. Correct this, it is not E0 upon m, it is E0 upon m omega, because integral of sin omega t dt is minus cos omega t upon omega. So in the absence of electromagnetic wave, when E0 is 0, if velocity of electron is 0, then constant of integration c becomes 0. If we assume that electric field is not present, E0 is 0, and we assume then the velocity of electron v is 0, then this gives the value of this constant c, which is 0. Then velocity of electron due to presence of electromagnetic wave, this velocity of electron becomes E0 upon m omega cos omega t. C is putting at 0. If at a particular height in ionosphere free electron density is n is electron density. It is number of electrons, free electrons per unit volume. Then current density due to this motion of electrons will be Je. It is the current density due to motion of electrons. It is minus NeV. Minus E is charge on electron. Capital N is number of electrons per unit volume. V is the velocity of electron, which is due to electromagnetic wave. Put this value of V, then current density Je becomes minus Ne square E0 upon m omega cos omega t. In free space, in the absence of electrons, displacement current density due to electric field of electromagnetic wave. This Je is the current density due to motion of electrons. We also have current density because the electric field is varying with time t, E equal to E0 sin omega t. So this electric field E is changing with time t. This will produce a current density also, and it is known as displacement current density, which we write as Jd. This displacement current density Jd is equal to delta D upon delta T, and D equal to epsilon 0 E. So it is epsilon 0 delta E upon delta T. This is because E electric field is changing with time t, and this current density is known as displacement current density Jd. Now put the value of E, which is E0 sin omega t, then this current density Jd becomes epsilon 0 E0 omega cos omega t. Differentiation of sin omega t is omega cos omega t. So we have these two current densities, Je and Jd. Je is current density due to motion of electrons, and Jd is displacement current density. So in ionosphere, resultant current density due to electromagnetic wave, resultant current density will be equal to sum of these two current densities, J equal to Je plus Jd. Put the value of Je and Jd, then resultant current density J becomes equal to minus n E square E0 upon m omega cos omega t plus epsilon 0 E0 omega cos omega t. Take this second term common, epsilon 0 E0 omega cos omega t. This entire second term is taken as common, and we write it as epsilon 0 into 1 minus n E square upon m omega square epsilon 0 into E0 omega cos omega t. Epsilon 0 E0 omega cos omega t is taken as common. Remaining term, which we write inside the bracket, is 1 minus n E square upon m omega square epsilon 0. Now we write this as epsilon E0 omega cos omega t. Here epsilon is written for epsilon 0 into 1 minus n E square upon m omega square epsilon 0. This equation, equation 6, which gives the value of epsilon, it is the permittivity of the ionized medium, and epsilon 0 is the permittivity of free space, that is vacuum. So this equation 6 represents permittivity of ionized medium. It is clear that due to presence of free electrons, permittivity of the medium decreases. From this relation, it is clear that epsilon is less than epsilon 0, because in right hand side we have epsilon 0 into 1 minus something. So epsilon is less than epsilon 0. So permittivity is decreased due to presence of free electrons, and this decrease in permittivity is epsilon 0 minus epsilon. Epsilon 0 is permittivity of free space, and epsilon is permittivity of ionized medium. Epsilon is less than epsilon 0, and the difference is epsilon 0 minus epsilon. Put the value of epsilon, which is epsilon 0 into 1 minus n E square upon m omega square epsilon 0. epsilon 0 is cancelled out and it will becomes equal to n e square upon m omega square. So this is the difference in permittivity, n e square upon m omega square. Velocity of electromagnetic wave in free space is given by c equal to 1 upon under root mu 0 epsilon 0. This is the velocity of electromagnetic wave. It is equal to the speed of light in vacuum. C equal to 1 upon under root mu 0 epsilon 0. For ionized medium, this velocity will becomes equal to 1 upon under root mu epsilon. So if we take the free space, we write mu 0 epsilon 0. If we take a ionized medium, we write mu and epsilon. Mu 0 and epsilon 0 are constants. Mu is permeability and epsilon is permittivity. Mu is permeability of ionized medium, epsilon is permittivity of ionized medium. Mu 0 is permeability of free space, epsilon 0 is permittivity of free space. And then this V becomes equal to 1 upon, this V is 1 upon under root mu epsilon. If in an ionized medium mu is almost equal to mu 0, then substituting the value of epsilon from equation 6, we have V equal to 1 upon under root mu 0 is written for mu, and for epsilon we use this relation epsilon equal to epsilon 0 into 1 minus n e square upon m omega square epsilon 0. Then velocity of electromagnetic wave in ionized medium becomes 1 upon under root mu 0 epsilon 0 into 1 minus n e square upon m omega square epsilon 0. From equation 8 and 9, it is clear that velocity of electromagnetic wave in ionized medium is greater than the velocity of electromagnetic wave in free space. This velocity V is greater than C, because C is 1 upon under root mu 0 epsilon 0 and V is 1 upon under root mu 0 epsilon 0 minus something. So in denominator we have the quantity less than under root mu 0 epsilon 0. So V is greater than C. Now we define the refractive index of ionized medium. This is the definition of refractive index, and it is equal to C upon V. Definition of refractive index, N equal to C upon V. C is velocity of electromagnetic wave in free space, and V is the velocity of electromagnetic wave in ionized medium. So N is equal to C upon V. C is actually speed of light in free space, which is same as speed of electromagnetic wave in free space, and V is the speed of electromagnetic wave in ionized medium. So if we put the value of C and V, this N refractive index will becomes equal to under root 1 minus n e square upon m omega square epsilon 0. C is 1 upon under root mu 0 epsilon 0 and V is given by this formula. 1 upon under root mu 0 epsilon 0 is cancelled out, and we get n equal to under root 1 minus n e square upon m omega square epsilon 0. So this n is less than 1 because we have under root 1 minus something. So this refractive index n is less than 1. If frequency of electromagnetic wave is f, then omega is 2 pi f. Charge on electron E is 1.6 into 10 to the power minus 19 coulomb. Mass of electron m is 9.1 into 10 to the power minus 31 kg. And permittivity of free space epsilon 0 is 8.86 into 10 to the power minus 12 coulomb square upon Newton meter square. If we put the values of these all constants, refractive index n will becomes equal to under root 1 minus, put the values of all these constants, then this will becomes n equal to under root 1 minus 81 n upon f square. Omega is written as 2 pi f. We put all the values of constants except n and f square. Then refractive index n is equal to root 1 minus 81 n upon f square. From this equation, it is clear that refractive index of ionized medium is less than 1. N is less than 1 and its value decreases with increase in ionization density n and increases with increase in frequency of wave f. So n refractive index will depend on capital N and f. If capital N increases, then small n will be decreases. Capital N is the electron concentration, density of electrons. It is the number of electrons per unit volume. And small n will increase if small f, frequency of radio wave or frequency of electromagnetic wave increases, then small n refractive index will be increases. So refractive index small n will depend on capital N, number of electrons per unit volume, and small f, frequency of radio wave, and it is less than 1. Now we will see what is the role of ionosphere. Role of ionosphere in propagation of radio waves. How these ionized layer of ionosphere reflect the radio waves coming from Earth's surface. So this ionosphere reflect the radio waves coming from Earth's surface and send them back to Earth's surface at another place. In this way, radio waves can be transmitted on Earth's surface from one place to another. Reflection of radio waves by ionized layer. Reflection of radio waves by ionized layer is actually due to refraction. Refractive index of ionized medium small n is given by this formula. Refractive index of ionized medium small n is equal to under root 1 minus 81 n upon f square. Under root 1 minus 81 capital N upon f square. Capital N is number of electrons per unit volume and small f is the frequency of radio wave. And we see that this small n refractive index is less than 1. Look at this figure. If this radio wave is incident on a ionized layer and angle of incidence is I and angle of refraction is R, then n is equal to sin I upon sin R. And from this formula, we see that n is less than 1. So, n is equal to sin I upon sin R and it is less than 1. So, I is less than R or R is greater than I. So, this angle of refraction R will be greater than angle of incidence I. And there are different such layers. In next layer, this angle of refraction R again increases, and this angle R continuously increases until it becomes equal to 90 degree. And when R becomes equal to 90 degree, then this radio wave will be reflected back to the Earth's surface. The phenomena like total internal reflection of light. In an ionized layer with increase in height, the electron density capital N first increases, hence the refractive index small n decreases. Small n depend on capital N, and with the increase in height, this capital N increases, so this small n decreases, due to which wave bend away from the normal. So, as capital N increases, small n decreases, this radio wave bend away from the normal. This angle of refraction R becomes greater and greater next time the refraction took place. If rate of change of refractive index with height is sufficient, a situation comes when refracted wave becomes parallel to ionized layer and then bends downwards. This phenomena is like total internal reflection of light. Finally, this wave emerges out of ionized layer with an angle equal to the angle of incidence and returns back towards Earth. At maximum point P of wave path of if ionizing density is Nm, ionization density, it is the density of electrons, number of electrons per unit volume. If at maximum point, if P is the maximum point, look at this figure, P is the maximum point of this path of radio wave. At this maximum point P, the angle R will becomes equal to 90 degree. At maximum point P of wave path, if ionization density is Nm, Nm is ionization density, it is the maximum value of capital N, small m is for maximum. Then at this point, angle of refraction R becomes equal to 90 degree, and if angle of incidence I is IC, then refractive index N is equal to sin IC upon sin 90. It is from the formula N equal to sin I upon sin R. I is IC and R is 90 degree. Then this N is equal to root 1 minus 81 Nm upon F square. We write Nm for N. It is the maximum value of N at this top point P. So, at this top point P, capital N is Nm, maximum value of capital N, electron density or ionization density, and at this point P, R is 90 degree, I is IC. Then we have n equal to sin IC upon sin 90, and it is equal to root 1 minus 81 nm upon f square. Sin 90 is 1, so we have n equal to sin IC equal to root 1 minus 81 nm upon f square. Now we will see what is the critical frequency. For a given ionizing layer, maximum frequency of electromagnetic wave which can be reflected back by it by normal incidence is known as critical frequency. Critical frequency is the maximum frequency of the electromagnetic wave which can be reflected back towards Earth by normal incidence, when incidence is normal. For normal incidence, it means I equal to 0. Angle of incidence is 0, then it is called as normal incidence. So I is 0 for normal incidence, then n, which is sin I upon sin r, will becomes equal to 0, and n is 1 minus 81 nm upon fc square from this formula. N is under root 1 minus 81 nm upon f square, it is 0. So we have 1 minus 81 nm upon fc square equal to 0, or 1 equal to 81 nm upon fc square. This will give the value of fc square. Fc square equal to 81 nm, and fc is 9 root nm. This fc is called the critical frequency. It is the maximum frequency of radio wave which can be reflected by ionized layer for normal incidence when angle of incidence I is 0 degree. Next is maximum usable frequency, MUF, maximum usable frequency, and we will find what is secant law. For a given ionizing layer, maximum frequency of radio wave incident at a particular angle other than normal, which can be reflected back by it towards the earth, is known as maximum usable frequency. So we have two frequencies. One is FC, critical frequency. It is the maximum frequency of radio wave which can be reflected back. And now we will find the maximum usable frequency. For critical frequency FC, it is the maximum frequency of radio wave which can be reflected back by ionizing layer, and it is for normal incidence. And this maximum usable frequency, it is also the maximum frequency of radio wave which can be reflected back to Earth's surface, but it is for angle of incidence which is not normal incidence, which means when I is not equal to 0. So this is MUF, maximum usable frequency, maximum value of frequency which can be reflected back to Earth's surface by ionized layer for incidence other than normal. For angle of incidence I, which is not equal to 0. From equation 2 and 3, equation 2 is this equation, n equal to sin IC equal to root 1 minus 81 nm upon f square. This is equation 2, and this is equation 3, fc equal to 9 root nm. So from equation 3 we have fc square equal to 81 nm, and we put the value of 81 nm, which is fc square. We put this value here in this relation. We put 81 nm equal to fc square, then we have sin IC equal to root 1 minus FC square upon F square. If we square it, then we have sin square IC equal to 1 minus FC square upon F square, or FC square upon F square equal to 1 minus sin square IC. 1 minus sin square IC is cos square IC. So FC square equal to F square cos square IC, or F square equal to FC square sec square IC. If we take the under root, then we have F equal to FC sec IC. FC is critical frequency and F is maximum usable frequency, and this is the relation between these two frequencies. FC is critical frequency. It is for normal incidence when I is 0. F is maximum usable frequency. It is for angle of incidence I which is not 0. And this is the relation between these two, F equal to FC sec IC, and this is known as secant law. For angle of incidence IC, F is the maximum usable frequency MUF. Equation 4 is known as secant law, which relates maximum usable frequency F and critical frequency FC. It is the relation between F and FC. F is MUF, maximum usable frequency, and FC is critical frequency. FC is the maximum frequency of the radio wave which can be reflected back towards Earth for I equal to 0 for normal incidence, and F is also the maximum frequency for which wave can be reflected back towards Earth's surface, but it is for incidence I not equal to 0. It is for not for normal incidence. For incidence which is not normal, I angle of incidence not equal to 0. Now we will see what is the skip distance. In this diagram, we have shown a point where transmitter antenna is put. Transmitter antenna will emit radio waves. These radio waves goes towards ionosphere, and this ionosphere reflects them and send back to Earth's surface. When there are different waves are shown 1, 2, 3, 4, 5, for which angle of incidence are different, and they will reach on Earth's surface at different points. This figure shows paths of radio waves incident on an ionized layer at different angles. For wave 1, angle of incidence is largest. For wave 1, angle of incidence I is largest. For wave 2, it is smaller. For wave 3, it is much smaller, and so on. As we move from 1, 2, 3, 4, 5, then angle of incidence I decreases. For wave 1, angle of incidence is maximum, largest, and it reaches at large distance from the transmitter antenna on the Earth's surface after reflection from ionized layer. Look at where this wave 1 reaches to Earth's surface. It reaches at large distance from transmitter antenna on Earth's surface after the reflection from ionosphere. But when angle of incidence decreases, wave 2 and wave 3, these radio waves reaches on the Earth's surface much closer to the transmitter antenna. Wave 2 and wave 3 reaches much closer to transmitter antenna. So we see for wave 1, 2 and 3, as angle of incidence I is decreases, the distance from transmitter antenna on Earth's surface where they reach, this distance will be decreases. If angle of incidence is decreased further, a situation comes when wave could not return back to Earth and moves upwards by crossing the ionization layer. This is for wave 5. For waves 1, 2 and 3, angle of incidence is reduced, so the distance on Earth's surface for these waves from transmitter antenna will decreases continuously. But a situation comes when if angle of incidence is reduced further. Look at for wave 4. Then this distance now is not decreases and it will be increased, and it will reach on Earth's surface at larger distance than the wave 3. And if angle of incidence is again decreased for wave 5, then it will not return to Earth's surface. So there is the minimum distance of reflected wave on Earth's surface from transmitter antenna. It is clear that wave 3 is inclined on ionized layer at an angle for which it returns back to the Earth's surface closest to the transmitter antenna. Its distance from transmitter antenna is known as skip distance. So we can define skip distance as follows. Skip distance is that minimum distance from the transmitter antenna at which a radio wave of given frequency returns back to Earth's surface after reflection from ionized layer. Frequency of radio wave corresponding to the 2 points of skip distance is maximum usable frequency. Let a radio wave of maximum usable frequency f is incident on ionized layer at an angle of incidence I. It returns back to Earth's surface at a distance d. Then this distance d is skip distance. It is the minimum distance from transmitter antenna. In this figure, we have shown transmitter antenna and receiving antenna. Wave is transmitted from T, transmitter antenna, and it is received at R, which is receiving antenna. Transmitter antenna T transmits radio wave. It goes to ionosphere and it is reflected by ionized layer, and then it returns back to Earth's surface at position R where receiving antenna is present. If the frequency is maximum usable frequency, then the distance between transmitter antenna and receiving antenna will be equal to skip distance. We write this skip distance as capital D. It is the minimum distance between receiving antenna and transmitter antenna. Now for this we have angle of incidence I, height from earth surface to this ionized layer is written as small h. Then we have from this geometry sec IC equal to this I is IC, then cos IC will be equal to base upon hypotenuse. Base is h for angle I, which is IC, and hypotenuse is under root h square plus d by 2 square. In this triangle where this angle of incidence I is shown, cos I or cos IC is base upon hypotenuse. It is h upon under root h square plus d square by 4. So sec IC will be equal to under root h square plus d square upon 4 upon h. It is 1 upon cos IC. So it will becomes equal to under root 1 plus d square upon 4 h square, dividing by h from numerator and denominator. Now according to secant law, F equal to Fc sec I or sec I equal to F upon Fc. So we write this sec I equal to F upon Fc, square it, which will give 1 plus d square upon 4h square equal to f square upon fc square, which will give d square equal to 4h square into f square upon fc square minus 1, or d will be equal to 2h under root f square upon fc square minus 1. This d is the skip distance.